Hello, in this video I am going to give you information about quantum mechanics which comes under module 4 of VTU syllabus. So here I am going to give you introduction to quantum mechanics and also explain Debroglies theory and Heisenberg's uncertainty principle. So now let us look at the introduction to quantum mechanics. So here let us take first what is black body. So black body is an object which absorbs all the radiations falling upon it and re-emit those radiations on heating it. So its absorption coefficient is observed to be 100%. So for example, hot filament, sun, etc. are all considered as black bodies. So here you can look at a chart. So here we are plotted a graph of intensity of emitted radiations from a black body versus the wavelength. So if you look at the chart, you can look at three curves here. So the first curve is taken when the temperature of the black body is 5000 Kelvin, and the second curve is at 4000 Kelvin, and the third curve is at 3000 Kelvin. So it is observed that the intensity of the radiation for a particular wavelength for which the intensity is going to be maximum considered as lambda max. So it is observed that the value of lambda max decreases as the temperature increases. That means it is shifting towards the lower wavelength side. So that's what the information that you are going to get from this graph. Next, if you look at the characteristics, for different temperatures of the black body, there are different curves. At a given temperature, the energy is not uniformly distributed the radiation spectrum. At a given temperature, the intensity of radiation increases in wavelength, that is lambda max. Its value is going to be maximum. With further increase in wavelength, the intensity of radiation decreases. The wavelength for which the radiant energy is going to be maximum, that is lambda max, decreases as temperature increases. So these were all some of the characteristics of the radiations emitted from the black body. And the next concept is Stephen's law. So this is also applicable to black body. So the total energy radiated per unit area from a black body is proportional to the fourth power of its temperature. So that means E is equal to sigma T to the power of 4. Here sigma is a proportionality constant considered as Stephen's constant. The value of sigma is found to be 5.67 into 10 to the power of minus 8 joules per meter square per second. Next, I am going to give you the details about Wien's displacement law. So the wavelength of maximum intensity emitted from a black body is inversely proportional to the absolute temperature of the emitting body, because of which the peaks of the energy curves for different temperatures get displaced towards the lower wavelength side. That means lambda max is proportional to 1 by T, or lambda max into T is equal to constant, which is equal to 2.898 into 10 to the power of minus 3 meter Kelvin. Next, Planck's radiation law. In 1900, Max Planck developed a structural model for black body radiation that leads to a theoretical equation for the wavelength distribution that is in complete agreement with the experimental results at all wavelengths. According to his theory, next, so the first point is a black body is imagined to be consisting of large number of electrical oscillators which are vibrating at discrete frequencies. The second point is an oscillator emits or absorbs energy in the form of discrete energy pockets known as photons, whose energy is an integral multiple of h nu, where h is Planck's constant and mu is the frequency. The third point is the energy emitted per unit volume per unit energy range is given by the product of number of modes of vibration in the given energy range and the energy per mode. The fourth one is, based on these ideas, Planck was able to derive an expression that agreed remarkably well with the experimental curves. It is given by u lambda d lambda is equal to 8 by hc by lambda to the power of 5 into 1 by e to the power of h mu by kt minus 1 into d lambda. This is known as Planck's radiation law. Here h is Planck's constant, c is the velocity of light, t is the temperature, and lambda is the wavelength, and k is the Boltzmann constant. Next, let us concentrate on what is Compton effect. So it is an effect which deals with the interaction between X-rays and electrons in an atom. When X-rays are incident on an electron, the scattered radiation will have the wavelength equal to or greater than the incident wavelength. So here X-ray of wavelength lambda is falling upon an electron and collide with it, then it gets scattered in a particular direction by making an angle theta as shown in the diagram. So let lambda dash be the wavelength of the scattered beam. So the change in wavelength, that is delta lambda, is equal to lambda dash minus lambda, that is equal to h by m naught c into 1 minus cos theta. So here m naught is the rest mass of the electron and theta is the angle of scattering. And if we look at the physical significance, Compton effect demonstrates the particle nature of electromagnetic wave or light. Next, now I want to tell you about Debroglies theory. So, by the law of symmetry of nature, a particle exhibits wave properties in addition to its particle properties. So, similar to that of electromagnetic waves, particles also exhibit wavy nature. The wavelength of the group of waves associated with particle of mass m moving with certain velocity v is given by lambda is equal to h by mv. So finally it will take another format, that is h by square root of 2m ev, that is equal to h by square root of 2mv. So these are all different forms of the equations related to the de Broglie wavelength lambda. When we look at the properties of matter waves represents the probability density variation in a region, and for a matter wave the psi value is equal to a sin kx cos omega t plus I sin omega t. This is a general solution to Schrodinger wave equation. And matter waves are neither transverse nor longitudinal, and their velocity is equal to that of a particle. And matter waves propagates as group of waves. Next, let us concentrate on what is Heisenberg uncertainty principle. So Heisenberg uncertainty principle states that it is impossible to determine both position and momentum of a moving particle at a given instant of time. So according to him, the position and momentum of a particle cannot be determined accurately and simultaneously. The product of uncertainty in the measurement of position, that is delta x, and the momentum, that is delta p, is always greater than or equal to h by 4 pi. That means delta x into delta p is greater than or equal to h by 4 pi. This uncertainty is not due to discrepancy with the apparatus or with the method of measurement, but because of the wavy, that is wavy nature of the object. This uncertainty persists as long as matter possesses wavy nature. Next, different forms of Heisenberg uncertainty principle. So the first equation is delta x delta p is greater than or equal to h by 4 pi. Here delta x is the position and delta p is the momentum. If we consider energy and time, the value, that is delta E into delta T, is greater than or equal to h by 4 pi. Here delta E is uncertainty in energy and delta T is the uncertainty in time. And the third equation is delta L into delta T is greater than h by 4 pi. So here delta L is the uncertainty in the angular momentum and delta theta is the uncertainty in the angular displacement. So these are all the three types or three forms of Heisenberg uncertainty principle. Next, if we look at the physical significance of Heisenberg uncertainty principle, it introduces the concept of probability. It can be used to find lifetime of electrons in an excited state, and it can be used to show that electrons does not exist inside the nucleus. Now, if we look at the application part of Heisenberg uncertainty principle, here we can concentrate on the non-existence of electron inside the nucleus. So, how Heisenberg uncertainty principle explains electron does not exist inside the nucleus. Now, let us consider a typical atomic nucleus with radius of the order of say 10 to the power of minus 14 meter. If the electron is confined within the nucleus, then the uncertainty in the position of the electron is of the order of 10 to the power of minus 14 meter. That is the diameter of the nucleus. So the uncertainty in the position, that is delta x, is equal to 10 to the power of minus 14 meter. Then the value of uncertainty in momentum, that is delta p, is equal to h by 4 pi into delta x. That is from Heisenberg uncertainty principle. So if we add the value of the Planck's constant and the value of the diameter of the nucleus, then the value of delta p, that is uncertainty in momentum, is equal to 5.26 into 10 to the power of minus 21 kg meter per second. So the value of delta p is equal to 5.26 into 10 to the power of minus 21 kg meter per second. If this is the uncertainty in the momentum, then the momentum p must be at least comparable with delta p. Therefore, the value of p is equal to 5.26 into 10 to the power of minus 21 kg meter per second. The equation of energy of the equation of energy from theory of relativity is given by E is equal to p square c square plus m naught square c to the power of 4 whole to the power of half. So this is the equation given by theory of relativity. So here it is observed that the value of m naught square c to the power of 4 is very much lesser than p square c square, and the value of m naught is equal to, that is the rest mass of electron, is equal to 9.1 into 10 to the power of minus 31 kg, and the value of c is equal to 3 into 10 to the power of 8 meter per second, and the value of m naught square c to the power of 4 is very much lesser. That's why it is going to be neglected. So finally the value of E can be written as p square c square whole to the power of half, and finally it will be equal to p into c. So substitute the value of p and c here, then we can able to calculate the energy E is equal to 9.9 million electron volts. So by looking at that value of energy, so electron to exist inside the nucleus, its energy must exceed 9.9 million electron volt. Experimentally, it is observed that during beta decay process, the beta particle emitted never have energy exceeding 4 million electron volts. That means the energy of the electron emitted during beta decay process is not at all more than 4 million electron volts. So because of this, we come to the conclusion that electron does not exist inside the nucleus. So Heisenberg uncertainty principle clearly proves that electron does not exist inside the nucleus. Thank you.